Hi, guys. Okay, so let's look at Chapter 8, Advanced Theories from the OpenStax chemistry book. And we will be covering hybridization in this video. And we will cover only 3 examples, but I'm going to cover more examples in my next videos. So we will look at Sp3, Sp2, and Sp hybridization. So before we start with the hybridization, let's understand what is the meaning of hybridization. Hybridization is basically mixing of the atomic orbitals. When these atomic orbitals mix, it's a linear combination of the atomic orbitals. When they mix, they result in the new orbitals, and these orbitals are called a hybrid orbitals. So the types, as I suggested, the ones that we are covering in this particular video is Sp3 is a hybridized orbital, Sp2 is a hybridized orbitals, and Sp hybridized orbitals. So what are the characteristics of the hybridized orbitals? They only form in covalently bonded atoms. That's one thing. Next is they also have the shapes and the orientation, just like the atomic orbitals, but since they are formed by the mixing of the atomic orbitals, their shapes and orientations are different from the atomic orbitals, but they do have them. Next is the number of hybrid orbitals is same as the number of the atomic orbitals combined. So for example, Sp3, that means S and the 3 of P's are combining. Sp2 means the S and the 2 of P's are combining. And Sp means that 1 S and 1 of P's are combining. So the number of atomic orbitals and the number of hybrid orbitals, that number matches. Now in a set are equal in energy. Now in a set, this is one set, Sp3 is one set. So all the atomic orbitals that have mixed and form the hybridized orbitals, they all have the same energy. Sp2, so the 3 orbitals have mixed, and in this case, we will see that all the 3 have the same energy and the shape is also the same. Similarly, the 1 of S and 1 of P have mixed, so in that case also, the energy is the same and the shape is also the same. Now, the orbitals that overlap horizontally or laterally, then they make the sigma bond, which looks like the colored, yellow colored sign you see on the screen. The unhybridized orbitals are the pure orbitals. In other words, they do not mix. And these orbitals, they form bonds by the sideways overlapping. So vertically or on the sideways, they make, or even the diagonally, they make these bonds which result in single bonds and, in double bonds and the triple bonds. Okay, so these are the pi orbitals, and you see the sign of the pi is the yellow colored symbol you see on the screen. Okay, now there is a certain process of doing this, making the hybridized orbitals. So I'm going to walk you through this, and then if you follow this strategy, you will never go wrong. First of all, always count the total number of valence electrons. Secondly, draw the Lewis dot structures. We've covered plenty of videos on Lewis dot structure. Please review them if you are not sure about how to do them. Okay, so do this part first. This tells you how many electrons are you dealing with, and what does the Lewis dot structure looks like. Now here, once you have made, you can also do the electronic configuration. At some point, I like to do the electronic configuration, and I like to make the energy diagrams. The reason is that it helps you to look at how many electrons you're dealing with. Okay, so anyway, so here you see, once you draw the Lewis structures, then you're going to count the electron pairs or the electron groups. These are also called the effective pairs, and some of the books also call them electron clouds. So whatever it is, it still means the same. Lone pair is considered to be 1 electron group. If you have 1 single bond or 2 single bonds or however many single bonds there are, that's 1 single bond is going to be 1 electron group. So if there are 2 single bonds, it would be 2 electron groups. If there are 3 single bonds, 3 electron groups. Okay, now if there is a double bond, then the double bond is still considered to be 1 electron group or 1 electron cloud. So if there are 2 double bonds, like in carbon dioxide, there are going to be 2 electron groups. A triple bond, like for example in HCN, carbon and nitrogen will form a triple bond. So this is still going to be considered as 1 electron group. So keep that in mind. Triple bond, double bond, single bond, lone pair, all of them constitute as each as one electron group. Okay, now one thing. Next is you are going to match, once you identify the electron groups, then you're going to match these groups to hybridization. So keep this in mind that if two electron groups are involved, it is always going to be sp hybridized. Sp hybridization, and the shape is going to be a linear shape. If there are three electron groups, then it would be Sp2 hybridization, and the shape is trigonal planar. If there are four electron groups, the shape is Sp3, and the hybridization is Sp3, the shape is tetrahedral. 5 electron groups is Sp3 D, and there are the shape is trigonal bipyramidal, and 6 electron groups is Sp3 D2, and the shape is octahedral. Okay, so that's very important. We will refer to this once we make the final molecule, the final structure, the hybridized one. So then we would look into, like, you know, what is their shape. So we'll come back to this point. Next is, based on the Lewis structure, you're going to count. You're going to count the number of sigma bonds, the number of pi bonds, and the lone pairs on each atom. Sigma bond is obviously the single bond. Now, pi bond means double bonds, and another pi bond also relate to triple bond. So you have to see how many pi bonds there are. And then there is a lone pair on each atom also. You need to keep that factor in as that. Now, as I said, it's optional for you to write the electronic configuration. On a personal level, I like to do it because these give you an insight into which electrons are we dealing with. So that's one thing. Next is drawing the energy diagrams. Also, these are optional but it's a very, very visualized way of looking at what's going on with the electrons here and which ones are mixing and which ones are free. So energy diagrams helps you to look into that, but you can, I mean, it's optional anyways. So here's the thing. Sp hybridization means that S and P are mixing. And remember that P has Px, Py, and Pz orbitals. So only Px has mixed, but Py and Pz are still pure. So they are going to be involved in sideways overlap, or, you know, that's why whenever there is Sp hybridization, we see that there is at least a double bond. Sp2 hybridization, here there is one S and two of P's are mixing to make the hybridized orbital Sp2, and we are left with just Pz. Pz is a pure P. Next is the Sp3. Sp3 is 4 orbitals are mixing. In other words, S, Px, Py, Pz are mixing, and there's no pure. Sp3D. Now remember, D is made up of 5 orbitals. Out of this, only one D is mixing with S, 1 of S, and 3 of P's, and the remaining 4 of the D's are pure. Then comes Sp3 D2. Sp3 D2 is total 3, 4, 5, 6 orbitals. 6 of orbitals are mixing, 1 of X, 3 of P's, and then 2 of D's, and the remaining 3 of D's remain pure. Now, once you get that, you are going to make the lobes. You're going to make the lobes for each atom, and you're going to place the electrons in each lobe. So Sp stands for 2 lobes, Sp2 means 3 lobes, Sp3 is 4 lobes, Sp3D is 5 lobes, and Sp3D2 is 6 lobes. So it's very important here. Next is, after you have identified the lobes and you have identified the hybridization, then you're going to just do the lateral overlap. Okay, so that lateral overlap is going to be first for the sigma bonds. You make all the overlaps with the sigma bonds, and then you do the sideways overlaps. And the sideways overlaps are for the pi bonds. And then look at the shapes of these electron group geometry. That's what we do. Now let's do these energy diagrams. Now these energy diagrams help, at least it helped me to see, you know, which electrons are being, you know, which orbitals are mixing and, you know, which ones are not. So anyway, so these are the energy diagrams. As we said, these are, let me just make this bigger. Okay. So here is this energy, and energy. This E stands for energy. Okay. And increasing form of energy. So in other words, S is lower energy than, you know, P and so forth. Okay, so here Sp3. Now Sp3, so this is This is, let's get back to this and let's bring this. Okay, so this is the S and this is the P's. These are the S, this is the P, this is the S, this is P, this is S, P, and D, and here you have S, P, and D. Okay. When, just imagine that right now we are just looking at the pure, these orbitals. In other words, we're just looking, I mean, obviously there are going to be electrons here, but for now, in this case, all four of them are mixing, all the four. So all four mix. And when all four mix, what happens then? Then the energy of the energy of the P's gets lowered, and the energy of the S is a little bit increased, but the P's is lowered. So once you have these, then you have a new orbitals which are Sp3D, Sp3. All four of them will form Sp3. These are the hybridized orbitals. Look at the next one. Next one is the Sp2. So here we have one of S and two of P's are mixing. These are mixing. Okay. So here we have one of S and two of P mix. So one of the P remains pure. So here we are not moving the P that is pure anywhere. It stays at that energy level, but the other two are brought down. And here we have S and the two of P's. So this becomes Sp2. And remember that one of the other P did not mix, so it stays at a higher energy level. Okay, so that's the P that is pure. Next is the Sp. Now, when we talk about Sp, we are only looking at the S and the P are mixing. Okay, so here one of S and one of P mix. And what does this mean then? Then we will have now 1 and 2. So these are the two hybridized Sp, right? And then your pure P, and that's why I'm not even changing the color, pure P's are 2. So 2 of the pure P's are still on the top. Okay, so this one is a P and this one is another P. So 1 of P and 2 of P's. Okay, now let's look at the Sp3 D. Now Sp3D is, in this case, 1 of S, Sp3, 3 of B's, and D, 1 of D's is mixing. So these guys are mixing. So 1 of S, 3 of P's, and 1 of D's mix. Okay. And so when they mix, what happens? After mixing, the whole idea is to lower the energy. So the new hybridized orbitals now have, sorry, that was a different color, now have these guys going to be slightly at a lower energy state, 1, 3 of P's, and then 1 of D. 1, 2, 3, 4, 5. Yeah. So this is Sp3D. Okay. And the 4 of the D's remain pure. So their energies don't change. 1, 2, 3, 4, and these are the D's. Okay. So remember that the hybridized orbitals will be at a lower energy state. Now we have the next is the Sp3 D2. So 1 of S, all the 3 of P's, and 2 of D's. So 1 of S, 3 of P's, and 2 of D's mix. And now what do we have? The 3 pure D's, which did not even mix, so they remain unhybridized. And we have the 1 of S, 3 of P, and 2 of D's. So this is the Sp3, Sp3 D2. Okay, so this is how this mixing and mixing and looks like. Now, in this case, when in the Sp3, now let me just write this down here. Let's grab another pen. Okay, so here, Sp3, 4 lobes. Okay, here, Sp2. Sp2 is 3 lobes. 3 lobes. Sp is 2 lobes. Sp3 D is 5 lobes. 1, 2, 3, 4, 5. 5 lobes. And Sp3 D2 is 6 lobes. Okay, so that's one piece. Next is, what do these lobes, what do they look like? Now here's another thing. Let's draw this. This lobes 1, 2, 3, and 4, like a tetrahedral shape. Okay, so these are these 4 lobes means they're going to be 4 sigma bonds. 4 sigma bonds. Okay, 3 lobes means 3 sigma bonds will be formed. 2 lobes means 2 sigma bonds will be formed. Sp3 D2, Sp3 D is 5 lobes means 5 sigma bonds is formed. And the other one is Sp3 D2 is 6 sigma bonds is formed. Okay, now these lobes, so we have these lobes. This is like a chair. The shape of this is like a chair. So the chair is one leg forward, one leg backward, one leg on the side, and one leg, I mean, like a 3-leg chair, like that. Okay, let me write down 3-legged chair. So this would be the scenario where the hybridized orbitals, they look like that. So, okay, 3 lobes. 3 lobes is going to be like a pizza. Like a pizza. Okay, so 3 sides. This makes the 3 sigma bonds, and it's like, how many lobes is that? It's going to be 3 lobes. 1, 2, and 3. So 3 lobes, Sp2, sigma bond. Okay, and this is like a triangle, a pierced triangle, or like a pizza. Sorry, Pizza. Pizza. Okay. Next is the Sp2. Sp is just 2 lobes. So the 2 lobes are like that. And these 2 lobes are like a rod or a stick. So it's more like a linear, like a rod, or it's a linear shape. So linear is like a line, and it's like more like a rod. Okay. Next is the 5 lobes, and that 5 lobes are going to be placed as like a skewer piercing a pizza. So here's the pizza. Sorry, again, change the color. Here's the pizza, and you have a skewer that is going in between and coming out like that. So like a skewer, skewer piercing the pizza. So that's the shape. It's very important you get these shapes correctly. Just have to erase this, sorry. Skewer pizza, SKEWER PIERCING, piercing the pizza. Okay, and this is so linear, like a rod. That's like a chair. That's like a like a shape is like a pizza. So when we draw the lobes, and how do we draw them? Do we draw them like this? One lobe going up, one going down, one going on this side, the other one this side, and then the third one here. So this is the pizza, like a shape is like that of a pizza. Okay, the last one is like a bread is being pierced. Okay, so like a pierced bread, P-I-E-R-C-E-D, pierced bread. And so just like you have a bread looking like a loaf, a small slice of bread, and you pierce it with something, needle or something, it goes top and bottom. So that's the shape of a octahedral. So octahedral is you just make these lobes on all the four sides, and then the up and bottom. So that you should be drawing it like this. So this is the octahedral shape. Octahedral. Okay, so I got these shapes. So first of all is the tetrahedral, Sp3. Sp2 is the trigonal planar. The Sp is linear. Then comes the trigonal bipyramidal, like two pyramids, one on top of the other, and that is the Sp3D. And Sp3 D2 is the octahedral shape. Okay, these are the basics of the energy diagrams.